Unopened. All right, welcome, welcome, welcome. Best day of the week, Mathursday. All right, so this is how it works. Hi, Shammy. Shammy? Yes. If you have any math questions or any topics you want to go over, just pop them in the chat and I will do my best to answer everything. Okay, so we usually try to stick with pre-algebra, middle school math through algebra 2, pre-calc, a little bit of pre-calc, but if you have anything beyond that, like a calculus question or anything like that, I can't necessarily help you in this forum, but what's really nice is that we have a great community, and so put your question in the chat, and somebody out there, I'm sure, will be able to help you out. All right, so we have percentages. Okay, so percents is one of those things that is just so essential for your everyday life, right? Like I deal with percentages, not just because I'm a math teacher, but I deal with percentages all the time. You're going somewhere for a sale. You're going somewhere and you have a discount, right? You're thinking about, percentages increases, inflation, all that kind of stuff. Percentages are really important. And percentages are also pretty straightforward. So a percent is really just looking at a ratio or kind of like, sort of like a fraction a bit. Ooh, sorry, that was so loud. Put this here. Okay, so percent means like every 100, right? So percent means per 100, right? So every 100. So it's a ratio. It's a ratio, but written in the context of being out of 100. Okay, so like 98% means 98 out of 100. Okay, now you can use this as like sort of thinking about it as a fraction, right? So if we think about it as a fraction, this is almost a whole thing, right? So this ratio, this percentage, it just makes it a little bit easier to work with when you're kind of like working with a decimal and things like that, right? Couple different ways that you can learn this. A lot of students will learn the percents just like as a ratio itself. So something like if you have, let's see, if you're looking for like 42% of, let's just do 40%. So 40% of 80, right? Now I know this is super straightforward, right? So what you look for is you've got 40% equals something out of 80, right? So you're looking at these similar ratios because what you're looking for is what number up here is 40% of 80. So thinking about like if 80 were 100, what would this be, right? It's sort of like a lot of teachers will teach this right after like fractions and things like that. Blank over 80, right? But you can also look at this as solving a proportion, right? So you would do cross multiplying, right? And you can do cross canceling. I know you can do that, right? That's fine. Okay, but if we just start off with just straightforward, right? So 80 times 40 is 3,200. Oops. Right? And 100 times, let's call this x. So we would say 100 times x. So x, we would have 3,200 equals 100 times x, okay? So that means that x is going to be 32. So out of 80, if we wanted to look at 40% of 80, 40% of 80, if we put 32 on top, those are going to be equivalent, right? So we would look at an equivalent here. Okay. All right, so Ben, what do you mean square root and fraction answer? Do you mean taking the square root of a function? Or I'm sorry, square root of a fraction? Okay, so Ben, you got to give me a little bit more. The square root and fraction answer. I'm not sure what that is going into. Okay, let's see. Square root and fraction is. Teach me all of pre-calc, please. I wish you know what, Abs? I wish I could do that in the next 45 minutes. That would be amazing, but not quite. The square root of something that can't be divided evenly. Okay, let me see. The square root of something that can't be divided evenly. And then, Shami, I'll do your compound area in just a minute. So, Ben, do you mean something like the square root of 27? Like where you can't just take the square root of 27. Are you talking about like simplifying a radical like that? Okay. So this is not going to necessarily give you a fraction answer. But what you want to do is when you're simplifying these radicals, you want to look for the perfect squares. So looking for factors of this number that are perfect squares. Okay. So 27 is 9 times 3, right? Now 9 is a perfect square. So I can take the square root of 9, but I can't take the square root of 3 without going into decimals, right? But I can look at the square root of 9 is 3. And then the square root of 3 is just the square root of 3. So that's how you would simplify this with that radical symbol and those numbers, right? Those values. So you would be looking for the perfect square, and then that's the way that they can get out from under the radical symbol is if you can take the square. So something like the square root of 50. So how would you simplify the square root of 50? So you can certainly just estimate, but it depends on what you're doing. If you're simplifying, right? If you're simplifying, then that is something different than finding the decimal, right? Or estimating, right? So looking at this, square root of 27, well, the next highest square root would be 36, and the next lowest square root would be 25. So we would say that this is a little bit over 25, right? Square root of 27 is a little over 5, okay? So square root of 50, if we think about what factors of 50 are perfect squares, well, we've got 25 and 2. So 25 can leave the square root and it becomes 5, right? But 2 can't leave the square root because it's not a perfect square. So this would be 5 root 2. So that's going to be the simplified version of this. Now, when is this useful? It's when you're doing like operations and things with radicals and you're combining them together. And there's a lot that goes into it with some trig functions and things like that. It's easier to work with it in this format than it is to work with it as a decimal, because these decimals are long and ugly and you really don't want to round very frequently, right? I always tell my students, like, rounding is the last thing that you do, right? If you can leave it as like square root of, 3 root 3 or 5 root 2, if you can leave it like that until the very end, It's going to give you a much more accurate number because if you think about, right, a much more accurate solution. If you think about it, like if you round and round and round and round, every time you round, you get a little bit further away from the actual answer, right? So if you don't round until the very, very end, you're going to be as close as you can be to the real answer, right? To the accurate, precise answer. But if you round and round and round and round and round, every time you do that, you're taking a little baby step away from the actual answer. Okay. You can do this process with imaginary numbers. Yeah, absolutely. So with imaginary numbers are when you have a root of negative, right? So if I had something like root, let's just stick with 50. Let's do root of negative 50, right? Now, those of you who are new to the channel may not realize this, but imaginary numbers were just made up so people could do more math, basically. Mathematicians didn't like that if you had a root of a negative number, you couldn't do any more math. So they said, you know what? We're just going to kind of like make up this little variable I, or this little code I, that said it's a -1. So square root of -1 is I. So when we look at this, we have -1 times 25 times 2. Okay. So the square root of -1 is I. Square root of 25 is going to be 5. And then we have square root of 2. So what this becomes is square root of -1 again is I. Square root of 25 is 5. I'm going to leave that up here. And then the square root of 2 stays as square root of 2. So square root of -50 is 5I root 2. So all that I does is it just takes out that square root of -1. And then you treat everything else exactly the same, right? Okay. Oh, so the -1 is just because you're kind of factoring this out. You're sort of like -50, we're just factoring this out, which means we're rewriting it as multiplication. Okay, so -1 times 25 times 2 is just because this was a -50. So here we did this with +50, right? Root +50. Here we did it with root -50. So the only difference is that we've got this I in there for that imaginary number, which again, I is just shorthand sort of for root -1. Okay. You did the state test today. What are integers? Oh, integers are numbers are like whole number, not whole numbers, but they are numbers that are positive or negative. So 3, 4, 5, they're counting numbers. They're the whole numbers, but they are also can be negative. So like -2, -3, +4, 5, 1,296, -5 billion. Those are all integers. Okay. Okay. Multiplying monomials. I can do that. Let's see. Okay. I just want to make sure. Let's see. Laplace transformation. Oh, no. No, Weston Fugit. Sorry, I can't do the Laplace stuff. Let's see. Would you mind after that to do? Yes, Shami, thank you. I'm going to do the area of compound figures. Okay, so with area, all right, I'm just going to stick with rectangles and squares because those are the easiest ways to do area, but you can also do this with any other figure, okay? So what we've got is if we have a figure like this, right? And there's some great things called area mazes that I love doing with some of the kids that I tutor. Oh, they're so fun, okay? So if we have something, we're gonna like this is obviously drawn freehand. Like these are rectangles, all the 90 degrees, right? All of that kind of stuff. Okay. So if I told you that this side is 10, right? This side is 5. This is 4. And this is 18. Okay. So what would the area be of this whole shape? Okay, so we've got 5, 4, 10, and 18. Okay, we've got 138. All right, Trevor, I'm going to get into that in just a minute, but I just made this up, so I don't know what it is. So 138, 148. Let's see. Oh, okay. Let's see here. 138, 128. Maybe 6 would be the missing side. Okay, good. So that's a good place to start, right? That 6 would be over here. And the reason we know this is 6 is because if this whole side is 10, this side is 4, that means that the rest of it is 6. Now, when we're finding the area of compound shapes or complex shapes, what you usually do is you usually divide it up into like manageable pieces, right? So what I'm going to do, now there are a lot of different ways that you could divide this up. Okay? I always encourage my students to like divide it up not in so many pieces that it's not manageable, but just enough, right? And whatever shape you see first. Like for me, I saw this first. Okay? So I saw that first as this little piece and then this whole thing, right? In which case, like it is important for us to know that this is 6, right? So then what I'm going to find is I'm going to find the area of this part A and this part B. And when I find those two areas, I'm going to add them together. Okay? So the area of part A up there is 5 times 4, which is 20. Okay. Now the area down here is not 10 times 18, it's 6 times 18, right? So 6 times 18, we could do, I'm just gonna use my calculator. 6 times 18, which is 108. Okay. And then I would add 108 and 120, or sorry, 108 and 20, and I get 128. Now, I didn't give you any units, right? Because we're just kind of making this up, right? So we've got units squared, right? Whatever those units are. So square feet, square centimeters, whatever it is, right? Yeah, so it's 128, right? Because you find the area of the two pieces. Now, even if I divided it up any other way, I would still get the same answer, right? So like here, let's just try it. If I divided it up a different way, right? So let's divide it up this way. So here and here. So now this side is 5 and this side is 10. So this would be 50, right? Now this side is 6, like we already figured out. So this part here would be 18 minus 5, right? Because this part is 5. So this would be 13 over here. And then I would check to see what 6 times 13 is, which is 78. Same thing, I do 78 plus 50, it's 128, right? Good. So you just want to find the area of each little individual piece. And again, this can work with circles, this works with triangles, this works with any shape as long as you divide it up with sides that you know, right? A bad way to divide this up would be if you did something like this, right? This would not be a good way to divide it up, right? Because I don't know where these lines are. I'm just kind of making these things up, right? So I'm not going to do that. I want to make sure that I divide it up with sides that I know for sure, okay? All right. So I see some trig. Yeah, that would not be a good way. Okay. Oh, that's wrong. Okay. Lucas, you're on break. There's a lot of people that are on break this week because they line it up with Easter. But we had our break like almost a month ago. Our spring break was the last 2 weeks of March. Okay, scientific notation. So scientific notation is a way of writing really big or really small numbers. Okay, so a couple of things. The first, you have like the first part, which is like all the digits. Now, those of you who are out there thinking like, well, it really depends on how many significant figures you have. We are not talking about sig figs here. I hate sig figs. I hate them. Okay. I understand the merit of them, I guess, because it's more accurate, it's more precise, blah, 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 blah. I understand. I know. I was a biochemistry major. I got it. I understand the importance of sig figs, but God, I hate them. Okay. All right. So 1.23 times 10 to the fourth. Okay. So this is a way of writing a really big number when it's just a little bit easier to work with this, especially if you're working with like multiple big numbers, right? So a couple of notes, okay? Here, this first part, okay, this first value, I don't know what letter they usually call it. We'll call it A, right? A needs to be less than 10 and greater than 1, okay? So it needs to be greater than 1, so it can't be less than 1, and it needs to be less than 10. So it can't be 10.0. It's got to be 9.9 or less, right? So this here times 10 to the fourth, this tells you how many ways you're moving the decimal, okay? Every time you multiply by 10 or divide by 10, right? You're moving the decimal. That's what our whole place value system is based on, is 10, right? It's based on powers of 10s. Tens, hundreds, thousands, tenths, hundredths, thousandths, 10,000s, right? On and on and on and on and on. So when we're multiplying by 10 to the fourth, 10 to the third, 10 to the second, whatever it is, you're moving the decimal that many spots, okay? So 1.23 times 10 to the fourth. Now 10 to the fourth, because this exponent is positive, it's getting bigger, right? 10 to the fourth is a really big number. It's a lot of zeros that you're multiplying by, okay? So then you're multiplying this 1.23 times 10 to the fourth. So what I'm going to do is I'm going to take my 1.23. This is to get like what the actual number is, right? And I'm going to move it to the right so it's getting bigger 4 spaces. I'm going to go, because this is times 10 to the 1, times 10 to the 2, times 10 to the 3, times 10 to the 4. And then I fill in with zeros, and I erase my original. So this number, 1.23 times 10 to the fourth, is 12,300. Okay? Now, more than likely, like you would just write out 12,300. That's fine, right? But sig figs, okay? Sometimes they'll change like what it needs to be, okay? All right, so let's look at it the other way. So if I have something like 6.04 times 10 to the negative 5, okay, 10 to the negative 5. So that means that it's a really, really small number, okay? So a really, really small number. So 10 to the negative 5. So now what I'm going to do, I'm still going to start out by doing my 6.04. Okay, but if you notice, I wrote it over here because I know my decimal, my number's getting smaller. It's sort of like dividing by 10 to the 5th. So I'm going to go to the left because it's getting smaller, 5 spaces. So I go 1, 2, 3, 4, 5. And then I fill in with my zeros. Okay, So this number is actually 0.00000604. Okay. Now where this comes in handy, where this is really useful, is if you are doing multiplication. Okay. So multiplication. Okay. Series to sigma and summations, that's a little bit beyond what we do here. Same with the multivariate kernel density. Yeah, that's, I mean, the questions, keep them coming, but those might need to be answered by somebody in the comments because that's a little beyond what we focus on here, okay? Trigonometry, we can talk about trigonometry. Logarithmic functions, do you give me a little bit more detail on that, Trevor? Are you talking about like calculus log functions or just kind of the basics of what a log is? Yeah, I can do trig if you're just talking about like right triangle trig and all the ratios and stuff like that. Okay, so if I have something, if I'm, 1.23 times 10 to the third times, let's do parentheses around this.
That's getting a lot of YouTube people today.
Ooh, 3.5 times 10 to the fifth. Okay, so here's what I'm going to do. When I'm multiplying these together, it actually doesn't matter what order I multiply things in, right? So it's the commutative property. It's like 2 times 3 is 3 times 2. So the order doesn't matter. Now, usually that's sort of like, yeah, I get it. The order of multiplication doesn't matter. But sometimes it's really useful, okay? Sometimes it's really useful, like in a situation like this, okay? Because I don't want to go through and look at 1,230 times, what is that, 350,000? Like, I don't want to deal with that. So what I can do instead is I can take these first numbers, since everything's being multiplied together, I can multiply 1.23 times 3.5 over here. And then I can multiply 10 to the third times 10 to the fifth. And then I can multiply it all together. It's basically keeping it in scientific notation. Okay, so 1.23 times 3.5 gives me 4.305. I'm not getting into sig figs, although this would be, I think, 4.3 is probably what it would be. So it would be 4.305 times 10 to the third times 10 to the fifth. I add the exponents together, so it's 10 to the eighth. Okay, so again, this is a really useful way that this is a huge number. I would not want to have to multiply that number together and like 0, 0, 0, 0. Like, that's bonkers, okay? So what we want to do is we can use this as a way to not only just write really large or really small numbers, but it's also to like work with those really large or really small numbers, okay? So graphing logs and graphing trig functions is really hard for me to show you guys in this forum. Because it's kind of hard to see the grid lines on these boards. So graphing, other than like graphing linear equations or graphing parabolas, but when you're talking about graphing logs, graphing like a little bit more detailed things, like those trig functions, it gets really tricky for you to be able to see. So I tend to stay away from those.
We have a couple of YouTube questions.
Okay, there's some YouTube questions.
Can I switch over to YouTube and you see that? I mean, I can.
Sure.
May I?
Yeah.
Okay, so Zozo has this one, which is Advanced Distributive Property for Algebra.
Okay.
That's 5 times 2x. I believe that's divided. No, it's a plus, I guess. 5 times 2x plus 5 times 3 equals 10x plus 15.
Oh, okay. So this is, I'm going to guess that it probably started out with 5 times 2x. Can you move that cursor? Move that. It's blocked. Yeah, there we go. 5 times 2x plus 3 equals 10x. Oh, wait. Well, this is going to be the same thing.
Okay, maybe.
So 5 times 2x plus 3, something like this, it does end up equaling 10x plus 15 because you distribute that 5, right? You would distribute that 5 through. 5 times 2x is 10x, and 5 times 3 is 15. So you would end up with that same thing. Now, what I'm going to do is I'm going to change this a little bit, though, because what if we had equals 8x plus 3. Okay, so now if we're doing this, now this gets to be a little bit more of like a solving the equation. So the first thing I would do right now, I would be probably given this equation like this. Okay, so when you're solving an equation like this, you want to simplify, then solve. So simplify both sides, distribute, common factor, like whatever, right? Whatever you need to do to simplify it, combine like terms, all that kind of stuff, then start solving. So I'm going to simplify by distributing that 5. Okay, so 5 times 2x is 10x. 5 times 3 is 15. And then we have 8x plus 3 because we haven't done anything to that side yet. So now that we've got this, I'm going to start solving. So I'm going to subtract 8x from both sides, and I get 2x plus 15 equals, that's gone away, so it equals 3. I'm going to subtract 15 from both sides. That goes away. I have 2x equals negative 12. Divide by 2 on both sides, so I have x equals negative 6. Okay, so then I could plug that back in up above, and it would work out. Okay, so hopefully that was helpful. I'm not sure what the, Zozo. Hopefully that was helpful.
Let's see, we're back to this. There's some geometry and algebra questions.
Oh, so with the unit circle, there are some like little tricks to kind of memorize it. But with the unit circle, here's the thing is that if you just memorize one of the quadrants, you can get all of the others, right? Now, you know it's 30, 45, 60. You know that. And then as long as you know that the hypotenuse is 1, you can actually figure out the rest of the unit circle and just kind of like memorizing the like root 2 over 2, root 3 over 3, whatever those are, right? 1/2, negative 1/2, all of that. But if you just memorize that first quadrant, and then as you're moving to the other quadrants, think about like, okay, here, you know, when you first start with learning the quadrants about the coordinate plane, you learn like positive, positive, negative, positive, negative, negative, and positive, negative, right? So if you can just remember I keep doing this with my hand because there is a little hand trick that you can do with like 30, 45, 60, 90. Yeah, so it'd be like 0, 30, 45, 60, and 90. So there is a way that you can do that. But then when you've got that, then you would kind of like flip it for over there, right? For over in quadrant 2. And then you can flip it for quadrant 3, right? But you can kind of like flip it around where everything's going to kind of work out. That's the only thing that I can say about the unit circle. Now, I always just offer my students like extra credit for memorizing the unit circle because I feel like it's sort of like the like a periodic table, right? There are things that you might memorize from the periodic table like by default, right? Like carbon is 12.011. That's what happens when you take a lot of chemistry classes. That's kind of where I'm at with that. Like with the unit circle, if you just pick up on the pattern, you'll be set for the rest of the quadrants and everything. Will it be on the Regents? I don't know if it's on the Regents. I don't know. I don't think they give you one. I know on the SAT they do not, but sometimes they will. Like if they ask you a question about the unit circle, oftentimes they will give you the unit circle and just kind of expect you to know what it is, right? Okay. All right, so trigonometry, Pythagorean theorem, ratios on triangles, and similar statements. There's a lot of trig. Okay, so let's just talk about trig ratios first. Okay, so we're just going to talk about trig ratios, right triangle trig. So the trig ratios, and these, even if you haven't learned these yet, those of you who are taking like PSAT or SAT or something like that, or if you're in Algebra 2 and you haven't gotten to trig yet, which you're probably going to be pretty close to it, pay attention. This is useful. Okay, so when we're talking about trig relates the angles and the side lengths in a triangle. Primarily, we focus on the right triangle because those are the ones that are kind of the easiest to work with right away, but you can use trig with non-right triangles as well, okay? If you get into like the law of sines and the law of cosines, because there are relationships. So everybody knows when you first learn about a right triangle, right? When you first learn about a right triangle, you learn the Pythagorean theorem, right? You know that a squared plus b squared equals c squared. You know that they always happen in that ratio, right? That relationship, okay? Now, what you don't always learn right away is that even though those side lengths are always going to be in that ratio, right? A squared plus b squared equals c squared. What is also true is that the angles, not the right angle, but the other two acute angles also will determine the ratio of the side lengths, okay? So trigonometry is where it starts to link angles and side lengths together with a triangle, okay? So when we're talking about the angle, we use this symbol called theta. Okay? It's like a zero, it's like an oval with a line through it, right? It's a Greek letter, theta. So theta is like our angle of interest. That's the angle like from the point of view that we're taking, okay? Now theta can be here or theta can be here. The one place it can never be is the right angle, okay? So we don't use the right angle for theta, but theta can be down here or it can be down here. The side that's across from your theta is your opposite. Okay? Now, if I had this like this, and my theta was up here, okay? This would be my opposite. Okay, so it's across from your theta. It's across from that, that angle that you're interested in, right? The side, the leg, right? The other leg that makes up the right angle is called the adjacent. Okay, so it's the one that's right next to theta. So then over here, if theta's up here, then this one over here would be my adjacent. Okay, now the one side length that's never going to change, it's always the same, is my hypotenuse. My hypotenuse is always across from my right angle. Okay, but the two legs might have two different names, right? So the adjacent and the hypotenuse, adjacent and opposite, and then the hypotenuse is always across from the right angle. Okay, so let's stick with just this one. I'm just going to clear this off for a little bit more space. Okay. Now the ratios, remember with Pythagorean theorem, we know it's a squared plus b squared equals c squared. That is the Pythagorean theorem, right? That's it. Now these ratios between the sides determined by the angle have specific names for them. So if we are talking about the relationship between the opposite and the hypotenuse, we call that sine. It looks like sin, but it's sine. Okay? So sine of theta, okay? So sine of that theta is the ratio between the opposite and the hypotenuse. Okay? Whatever that theta value is, that is going to be like, that's the same ratio no matter what. No matter what the side lengths are, they're going to happen in the same ratio, depending on what that angle is. Okay? Now, if we're talking about the ratio between the adjacent and the hypotenuse, that also has a name. It's called cosine. Okay? So cosine theta, oh, I'm not going to have enough room here. So cosine theta is going to be the adjacent over the hypotenuse. Okay? And again, depending on what that theta is, we've got this. Right? And then the last one is between the opposite and the adjacent, and that is called tangent. Okay, so tangent theta is the opposite over the adjacent. Okay, easy way to remember this is SOHCAHTOA. So we have SOHCAHTOA. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. Okay. Giovanni, I'll do algebra inequalities in just a minute. Okay. Those are the right triangle trig ratios. That's what we've got. So if there's any other specific questions that you have, then put them into the chat and I can get to those, but that's kind of the basics for just like the right triangle trig ratios. Okay. Oh, the inverse, do you mean the inverses like secant, cosecant, and cotangent, or do you mean sine -1? So secant, okay, secant, cosecant, and cotangent. So the inverses, those are not useful at all. They're really not useful at all, okay? They're just so you can do more options with those, but it's not really that big a deal. So with the inverse functions, hold on. With the inverses of these, okay, I'm just gonna use the back of this board because I'm running out of boards tonight, guys. Okay. Yeah, they are just like the 1 over whichever function, but so like sine theta, the inverse of that is cosecant. So cosecant theta is the hypotenuse over the opposite. That's it. Secant theta is the inverse of the cosine, so that is hypotenuse over adjacent. And then cotangent theta is the adjacent over the opposite. Okay. So those are the 6 trig ratios right there. I know they are not technically the inverses. These are the reciprocals. These are, because when you talk about the inverse trig functions, which is why I kind of asked for the clarification. When you're talking about the inverse of these trig ratios, you're actually talking about something like sine to the -1 power. Okay, and what you use that for is you use that if you did sine -1 of the opposite over the hypotenuse, that is going to give you your theta value. So we use that sine -1 or that inverse sine or arc sine. There's a lot of different names for it, but you would use that to figure out the angle measurement. So everybody kind of calls these the inverse trig ratios, but they're not technically, right? They're just like the reciprocals and they're just the other ratios. But really I've moved away from asking my students to find all 6 of them because you don't really come across these that much other than when you're given that information, right? So I really just stick with the sine, cosine, and tangent because I think cosecant, cotangent, and secant, they will come more into play further down the line. But really, like this, working with this is challenging enough to begin with. So other than just knowing that cosecant is the upside down of sine and secant is the upside down of cosine and cotangent is the upside down of tangent, there's nothing else to really know about it. It's not much. So theta is sort of like a variable like x. It's just talking about an angle. So it's a specific angle, and we call it like the angle of interest. That's like the angle you're paying attention to or the angle that you're looking from, right? Yeah, so theta is more like an angle. It can, you treat it like a variable, but it can also have a value. But you can use it, like you can manipulate it and move it around in an equation like a variable too. Okay, let's see. We have time for one more thing. I think there was one thing that we were talking about. What was it? Oh, algebra inequalities. That's what it was. Algebra inequalities. Got it. Okay, so solving an algebraic inequality. And Giovanni, is that Giovanni or Giovanni? Giovanni. Let me know if this is what you're kind of looking for or not. So with algebraic inequalities, so when you have something like 3x plus 5 is greater than 11. Okay, so something like that, right? When it's set up like this, or even if it's more complicated than this, ultimately, if you're trying to solve an inequality, you solve it just like an equation, with one exception. Okay, but again, you solve it just like an equation. The one exception, you just solve for x. Yep, just like if this were an equal sign. The only exception to that is if you are multiplying or dividing by a negative number, you flip the sign, the direction. That's it. So like something like this, I'm just gonna go I'm gonna solve this just as if that were an equal sign. So minus 5 cancels out. I have 3x is greater than 6. Divide by 3, cancels out. 6 divided by 3 is 2. That was not a negative number, so I'm going to leave the sign exactly as it is. So x has to be greater than 2. That's it, right? That is it for solving algebraic inequalities. So again, that is the only thing that you need to worry about is if you have something, so if I had, well, let's do just like a very similar one, right? If I had, let's change this up a little bit. What if I had that 5 minus 3x needed to be greater than 11? Okay. So the only thing that's changed is that this is, I kind of switched the order and made this a minus 3x. Okay. So again, I'm going to solve this just like a normal equation. I'm going to subtract 5. That cancels out. I'm left with negative 3x. I haven't done anything to that yet, is greater than 6. And now I'm going to divide by negative 3. Red flag. Not really a red flag, but warning, right? You're dividing by a negative number. So now when I'm multiplying or dividing by a negative number, I switch the direction of the sign. So now I've got x is less than negative 2. Okay. So x has to be less than negative 2 because I divided by a negative number. It's the only time you have to do that. Okay, so other than that, you solve it just like a regular equation. You don't have to worry about flipping the sign until you until you divide or multiply by a negative number. Okay. Okay. Yep, if you multiply by a negative number, yep. So it's multiplying or dividing by a negative. That's when you flip it over. Will a sign flip over multiple times? I mean, I guess if you're, if so it won't necessarily flip multiple times if you simplify both sides and then solve. But if you're not simplifying, there might be like, oh, and then I'm going to divide by this, but probably not. And then I'm going to multiply by this. More than likely, it would just be once, but I'm not going to say it's never going to happen. Okay, so I'm not going to get into hyperbolas tonight, but we might be able to do that next week. Yeah, I mean, basically graphing anything, no matter what the equation is, you can either use your graphing calculator and get your values that way, or you can pick values for X and plug them in and solve for Y. You can always figure out what that is. That works with every single line graph that there is. Okay?
There are a couple other really simple questions on YouTube, like one about 8th grade probability tables and another 6th grader honors about fractions. If you have those within your wheelhouse. If not,
I mean, I do, but probability tables are a little more advanced.
Okay.
But we can add them to the list for next week.
Sure.
All right, guys. So if you are needing more help with things, check out my library of videos. I have a whole lot of videos on different topics, especially, I see quadratics. Those are on there a lot. I do quadratics pretty much every week, except this week. Look at that. So click the link and do the stuff. Have a great night. We will be posting some information about summer opportunities and things like that. But of course, if you're looking for any tutoring or anything like that, click the link and do the stuff. All right. Good night, guys. Oh my God, I'm so hot.
I know. You need to take a breath before we do